Hello everyone, I'm Timothy Crump from the University of Manchester, and I'm going to present to you today a mesoscale approach to modelling dynamic fracture under rate dependent loading. In particular, I'm going to try and show a benchmarking of an approach that shows promise at looking at things that my project related to. In particular, lifetime extension of the UK's nuclear reactors, and we're looking at dynamic effects of initial cracks within the moderator bricks, which provide the structural integrity to the AGR cores, and so therefore we're looking at energetically conservative manners of looking at crack propagation in dynamics. So, I'm sure you all know this already, but a brief overview of elastic dynamic fracture. Three particular things going on. You've got a propagating crack dynamically, you've got a dynamic system, and then you've got the velocity hardening that occurs due to different GCs or fracture toughness is at initiation. In particular, you can notice we go from a region where the stress initiation is dominated by maximum stress, whereas in the propagation it's due to the bulk material properties. So we're looking for something that's able to cope with this phase transition, as it were, between something that's slow and something very quick. So from this, there's an approach that I'm considering called the extended finite element method with cohesive zones, as you may know as well. It takes something that we consider to be mesh independent, and instead of having a damage parameter at the crack tip, instead we take a cohesive law which is phenomenologically sensible in comparison to the velocity hardening. In particular, we allow the opening rate of the crack to be connected to the opening of the crack to be connected to the opening rate, so we have a smooth dynamic crack opening, so therefore the loading from a first dynamic crack is sensible. We implement this into a code known as Code which is EDF Energy's in-house finite element solver code, and in particular we use a quasi-explicit solver in an algorithm that is able to update through the cohesive forces the crack as it propagates through a undulating dynamic potential. The quasi-explicit solver in particular is quite useful because it allows us to integrate through the JKCOD crack opening displacement equivalency a local problem into a global system, energetically conservatively in a linear elastic fractional mechanical system. We use a simple bifurcation criterion, the ranking criterion for a smear crack tip to ascertain the stresses ahead of the crack. But in general, the quasi-explicit solver simply takes an implicit solution and uses that as a forcing term to force the explicit part of the global dynamics to be energetically conservative per each time step of propagation. We use a set-valued cohesive law to allow it to be discretized, so therefore through a Lagrangian neutral-Raphson method we are able to ascertain at each step the correct energy state from the cohesive crack as it propagates. So, to benchmark it, what's out there for me to use? We have, as via a fund many years ago, we have a 1D analytical solution based actually on a cohesive zone approach in a double cantilever beam where we know the geometry shape, so therefore we can do a full integral of the whole global dynamics of the system. Nicely, this comes down to a very simple arrest length, which is n to the quarter of the original crack length, and we are looking to solve pretty much that equation on the top right for the crack acceleration. In 2D, it's very simple to do. The top right-hand graph, the two purple lines are the two unadjusted and the adjusted dynamic crack speeds for a crack propagating. The adjusted one is for the strain waves that interact with the crack tip as it propagates. Under two different loadings, we're looking to see if the loading rate of the crack of the system affects the crack propagating speed. This one is just on the static loading, and as you can see, the black line. The black line here, which is the experimentally observed crack speed in the experiment, is equivalent to the adjusted analytical speed, and also what we're observing was the explicit solver in XZ. Then under a small impulse loading, we also get to the point where we expect under these effects crack branching to possibly occur, which is about 0.7 of the CR, and that occurs at the time that it was observed for the branching to occur within the experiment. So we're in the right region of what we expect to see. So this being good news, putting it into 3D, looking at possibly bifurcation angles due to macro strain waves, and just doing a quick parametric study to show you the effects of initiation energy and what happens as the crack propagates. So under 3D, same experiment again, without any crack branching criteria, just a bifurcation angle from Rankine. We ascertain for the correct stress intensity factor that the appropriate angle within 0.1 of the angle for the half branching angle, which is equivalent to what we see in the experiment. And this is for this crack here. If we iterate the solver over it more and more, we get a smoother crack shape, but for demonstration purposes, I made quite a coarse profile here. As you can see, as we go a smaller and smaller initiation GC, i.e. the material becomes less and less brittle in this sense, we have a crack which has less momentum in essence. The crack at the beginning has less energy to maintain its propagation through the strain waves. We start to see a second bifurcation again, which in other experiments we have seen as well, secondary bifurcations. So this is also looking quite promising. So what use is this to my project? Great that we can benchmark it, it makes sense with some theoretical approach, some experiments out there. But in particular, it seems to be quite useful when looking at a graphite brick. Under pretty much any loading, we can look at different scenarios. We can look at a crack shape which is close to the fracture criterion, which is very equivalent to the quasi-static shape we've seen with just a standard external approach, under a lot larger loading, which gives us an interesting interaction due to K1, K2 and K3, and in particular what I wanted to look at, which is further fragmentation of the component, or i.e. secondary cracking due to strain rate. And it's really key to note that the quasi-explicit solver is useful for this because the waves we produce from the initial crack are energetically conservative, so therefore we can look at possibly some initiation secondary to that. So for some conclusions, we can say with a benchmarking experiment, this is a reasonable approach to start looking at an industrial problem, and under several different loadings, it's shown in a simple double cantilever beam that I was able to predict with reasonable accuracy experimental results. My further work will be to implement this so we can fully look at full fragmentation model. And also, as will be discussed, I'm sure, over the next couple of days, is the applicability of quasi-static fracture criterion to a dynamic problem. As you notice, I kept sigma c constant, but we know it's only going to contribute up to 10 to 15% of the energy to the system. However, it's still something that's quite significant when we're looking at strain waves that may interact with the propagating crack. So, thank you very much. Do you have any questions?